So now that we are done with the summarization and visualizations, we can now start talking about doing the hypothesis test as well as confidence intervals within R. So what's nice is, again, you had to always run stack poly package. Great, cool. It's not as bad as installing it. However, in terms of running a t-test, two independent sample mean t-test, use this t-test function. You would then have your response variable be first, and you're not going to use quotations, so no, you don't use quotations. Then you use tilde. Okay, it's going to be your response variable, tilde, then your explanatory variable. For most of the functions that we're doing in this class, it's going to be in that similar format. Okay, so it's going to be your response variable, tilde, your explanatory variable. So your gender is explaining what's happening in your gender in your gain weight, and we're still using the data set from King County. So what happens here when I run this is that I get a t-test, I get a hypothesis test as well as a confidence interval. So that's kind of cool. So let's look at our results. Let's see what it says. Make this a little wider. Okay. So this right here is going to be my test statistic. This is the true value, the true approximation, or at least not true approximation of the degrees of freedom. And this gives me my p-value. Okay. And this tells me what my alternative hypothesis is, that it's not equal to 0. The difference between the two groups is not equal to 0. And then it gives me my confidence interval here, okay, for the difference between the two means. And then finally, it gives you your mean for males and the mean for females. So that's interesting. That's cool. All right. So then what should you do to your null hypothesis with such a large p-value? You should fail to reject your null hypothesis. And notice 0 is in between the lower bound and upper bound, meaning that 0 is plausible for the difference between the two groups. However, let's assume that the actual variances are equal. That means that we'll be using a pooled variance, and we spoke about that in class. So the only thing that's different now is that all you have to do is say var.equal is equal to true. So that's all you have to do different. And then here you go. Your test statistic is quite similar, but a little bit off. But at the end of the day, as you can see, the degrees of freedom is calculated as such. Your p-value is slightly smaller, but at the end of the day, it's the same conclusion. So if you go back to the variances before, you would have saw that at least standard deviations, they're very similar. So ideally, you would do something like this, or the pooled variance actually in this situation. Okay. Now, let's say I'm interested in paired data. Remember the paired data example? So let's say we're looking at GPA as our response and the quarter as our explanatory variable, right? It's explaining the quarter is explaining the variability in the GPA. We go ahead and have data is equal to GPA data, but look at this difference. Now we're going to say that pair is equal to true. Okay, that's going to be pair is equal to true, and then that now performs a paired t-test. So here it says, as you can see, this says paired t-test. Before this said 2 sample t-test. Here it said Welch 2 sample t-test. So those are the indicators what tests you're doing. So this is the paired t-test. Look how large. This is my test statistic. Everything is almost the same. This is my test statistic. This is my degrees of freedom. This is my p-value, really small, telling me that there is a difference. As you can see, my alternative is that the true difference there is not, the true difference in means is not equal to 0, okay? And then here you see that 0 is not in between the lower bound and upper bound, and this is the mean of the differences. And the reason why this is positive rather than negative, they did spring minus winter instead of winter minus spring, okay? But it doesn't matter in terms of results. So that's how you would implement, at least getting the calculations within R. Okay, so in terms of critical value, however, we still need to talk about that. So let's say I've been charged to find a 95% confidence interval. R alpha is equal to 0.05, and I'm doing a two-tailed test. That means that this is 0.05. I do 0.05 divided by 2. And the reason why I do that is because it's a two-tailed test, or it's because it's a confidence interval, so it's divided by 2, and I do 1 minus that. When I run this, if you want to see what this gives me, this is going to be 0.975. So that's what I'm going to input into Qt. And then my degrees of freedom, I'm assuming I'm still using paired, but you put the degrees of freedom, whatever you got from your t.test. Okay, so when you run this is going to give you a critical value, 2.000995. Okay, similar logic here, and this is a little bit off, but alpha in this, or at least you're creating a 99% confidence interval. That means alpha is equal to 0.01, right? And so when I run that into this calculation, I should get 0.995. Okay, and that's what I'm going to then put into this function. Should this be smaller or larger than 2.00095? Think about it. It should be larger. It's going to be larger. Okay, and rationale for that is because you have more confidence. Okay, and so that's how you find your critical value. It could be used in the hypothesis test, or it could be used in confidence intervals. So hopefully that helps, and yeah.